All right, so welcome to your next integration technique that we're going to learn. It's another foundational technique that we're going to need to use probably throughout the rest of this class, and if you go on to take any sort of multivariable calculus course where you're doing integrals again, then integration by parts is just a pretty foundational technique that we're going to need to have in our toolkit. Much like U substitution. And so, so far we have learned how to integrate things that look like x squared, for instance, right? We've learned how to deal with the power rule from taking derivatives. We've also learned how to do stuff like 2x plus 3 divided by x squared plus 3x. This one is, we recognize maybe that the chain rule has taken place, and so we could do a U substitution to help us out here. And so the next one that we're going to tackle really is, we did power rule, chain rule. Probably the next most prevalent derivative rule that exists is going to be the good old-fashioned product rule. Okay, and so this video basically, what integration by parts does is it kind of uses the product rule to help us address a very particular type of integral. And this integral that we're going to be covering is very common. So the integrals that we're going to be interested in are integrals, for instance, that maybe look like x multiplied by sine of x dx, right? Where I'm looking at this thing and thinking to myself, well, I know how to integrate x by itself, and I know how to integrate sine of x by itself, but the product of these two things I don't necessarily know how to integrate, right? What function has a derivative that is just equal to x times sine of x? Off the top of my head, I'm not quite sure, and I alluded to it in previous videos that we can't just take the integral of the first bit and the integral of the second bit and just multiply them. It doesn't work. You can try if you'd like to pause the video and try it on your own just to verify that doesn't work. So we're going to need a special rule that helps us address, right? What if I have some function here and some other function here that are being multiplied together, and I want to try my best to integrate those things? So that is what we're going to do in this video. And just to kind of, now that we've kind of set the table, so to speak, I want to give you some intuition behind the theory about where this method kind of comes from. So, we're going to need to remember what the product rule is. Okay, so we're remembering the product rule. Okay, now in the textbook, they use the letters U and V to represent these functions. I usually use, F and G when I teach the product rule in Calc 1, right? But I will use U and V to kind of match along with the textbook. So the idea here is that we're going to say, let's let U, and X and V of X be functions, okay? Right? I'm not going to write U of X and V of X every single time. I'm simply just going to say, then if we were to take the derivative with respect to X of the product of these two functions. So if I put U in here and I multiply it by V, we need to remember kind of what it is that we're going to get out. And so, right, the idea is that we leave the first function alone. Or if you want, right, it doesn't really matter the order. Well, we can do it, the derivative of the first function. So we're going to have the derivative of the first function. So in this case, the derivative of U. And then we're going to multiply that by the second function, so V. And then we're going to add, and then we have the first function by itself, and then multiply that by the derivative of the second function. And if this looks a little bit strange, it's probably just because you've seen it as U prime times V plus U times V prime, okay? And the idea here is I'm just going to rewrite what I have here in pink. I'm just going to rewrite this as, well, so we still have d dx, right, the derivative of U times V, is equal to du dx times v plus u times dv dx. Okay, great. So this is the product rule fully executed. It's ready to go. And since the goal, since our goal more or less is to figure out how to integrate the product of two functions, then what we're going to do very naturally right now is we're just going to take the integral of both sides with respect to x. And we're going to integrate this entire right side with respect to x. Okay. And so what do we get on the left-hand side? Well, the left-hand side, right, what is the antiderivative of the derivative of something, right? If this is the derivative and this is the antiderivative, then, well, they should cancel out, and that should just get us back to the u times v that we originally had. Now, on the right side, we're going to get two different things, right? This dx is going to distribute to kind of both terms in the sense that we're going to have two integrals that I could write down. So I'm going to have integral of du dx times v, and then dx, plus the integral of u times dv dx dx. Okay, so all I did was split the right side into two integrals. It's a good idea, right? Maybe I should have put some parentheses here just to make it clear I'm taking the integral of the entire right side. And let's see, what do we have going on here? Well, dx is like an infinitely small change in the x direction. Dx here is an infinitely small change in the x direction. And those dx's will cancel out, right? They're just going to cancel out, and they're going to leave us with kind of something interesting here on the right side, where we're just going to have the integral, and I'm just going to swap the order, but this dx and that dx is going to cancel, and we're going to have v times du plus the integral of u times dv, again, because this next bit of dx is going to cancel out, and we're left with this. Now, at this point, people are kind of wondering, they're like, all right, I don't understand. Why is it this complicated? What's going on? Bear with me. We're almost at the punchline, okay? So remember, just let's kind of go back to the start and make sure we're all on the same page here. So we started off with the product rule, right? And now the idea is that we are trying to solve an integral that looks like integral of the product of two functions. I have one function here, I have it being multiplied by some other function here, and then with like a dx, we'll say at the end, or whatever variable it happens to be with. So I'm looking for a formula that has the integral of two functions, right, equals stuff. I want a formula that tells me if I get something that looks like this, what is my answer going to look like? And so I said, well, since we're doing the product of two things in that integral, maybe it's appropriate to start with the product rule from calculus. And so we did that. And now we took the integral of both sides just to see what would show up. And now, in taking the integral and simplifying the left-hand side and distributing it, right, making two integrals and distributing in that dx, we're now at like this very interesting point right here, which is that, now I do sort of have, at least one integral, right, that looks like, I have something multiplied by something else, right? I have the integral of two things being multiplied together. And you may, be wondering, you say, well, dv is not itself a function, is it? And say, sure it is, right? Because, don't forget in the video that we covered for u substitution, for instance, if we were doing the integral of 2x plus 3 over x squared plus 3x dx, if I go ahead and I say we're going to let u be equal to x squared plus 3x, then du dx was equal to 2x plus 3, and we could write this as du is equal to 2x plus 3 dx, right? So du itself is like a function and then multiplied by a dx. So this du is probably equal to some function multiplied by a dx. Same thing with this dv over here. It's going to be equal to some function times a dx. And so, it doesn't look like it, and it may seem a little bit strange or weird, but this is, kind of what we're looking for. Specifically, this part right here, right? And I could use either one of these. They're both, the product of two functions, I claim. But I'm going to use this one, and I'm just going to rearrange everything that we have to get this little formula here. So I'm going to write that on the left side that we're going to have u times v minus the integral of v times du is equal to the integral of u times dv. And this thing, I'll put my little squiggly line around it. This right here is our, or I'll say instead of how, just our kind of formula for doing what's called integration by parts. Integration by parts, aka the product, integrating the product of two or more functions, but we'll say two functions for now. Okay, this is our formula, and it looks a little weird, and not only is it weird because right here I have the product of two functions, like that's great, but what's also weird is that inside of it I still have another integral, and that integral in and of itself is the product of two functions. So how on earth are we supposed to be able to use this thing? Allow me to demonstrate. So we're going to start off with a relatively simple example, very classic example in the textbook. It's going to be the example of that I illustrated earlier, which is how do we do the integral of x times sine of x dx, right? How do I go about doing this? Okay, I have the product of two functions. How do I do this? Well, I claim that we're going to use this particular formula, right? We did all this work, and so hopefully it ends up being useful. And so what I'm going to do is, what this formula says is that if I have a u and I have some dv, then all I need to solve this thing, right, would be, so number one says we need a u, and step two is we need a dv, right? But the idea is right, if I have the u and I have the dv, right, then I just need like a few more pieces to really make this formula work. And so what does that mean for the context of this problem? Let's just roll with it for a second. Let's pick my u to be this x that I've selected here. So let's say let's let my u be equal to x. Now, just starting there, right? If I have u equals x, what else can I get from this? Well, hopefully from the integration, or excuse me, from the u substitution video, right, we saw that if I took the derivative with respect to x of both sides, so of u, and the derivative with respect to x of x, on the left-hand side, I get du dx, and on the right-hand side, I just get 1, and then from this, I can get the very nice du is equal to just dx. That's the relationship I get. And so all of a sudden, now I know what my du is. I've unlocked what my du is by making a selection for u. So I'm going to just erase this just for the sake of space and just say that if I've picked my u to be equal to x, then my du is going to be equal to dx. Okay, that's great. And now what do I pick for my dv? Well, dv has to be everything else that's left over in the problem. I can't have anything else dangling, right? I wouldn't just say dv is just equal to sine of x, because then what do I do with the dx? So my dv is actually going to be equal to everything else that's sitting there. So I'm going to say, so we said let u equal x, and we're going to say let's let dv be equal to sine of x dx. And this, again, shouldn't look very, scary, because going back to this problem here with the u substitution, we're very used to having, a du equals to something times dx, right? Or if this problem was in turn, if we did a v substitution, it'd be dv is equal to 2x plus 3 dx. So this is not, anything out of the ordinary, totally okay to have. And again, if I have this, then in theory, I can get, what v is equal to, because all I have to do is to take the integral of both sides, and we're good, right? The integral of dv is going to get me v, and all I have to do now is answer the very simple question, what is the integral of sine of x? And the integral of sine of x, or the antiderivative of sine of x, is going to be negative cosine of x. And so at this point, right, maybe I'll put a box around all of this stuff. At this point, we have all of the tools that we need to use this formula that we came up with earlier. Remember, this formula says you pick your u, you pick your dv, and as long as as long as you can get your u, which I already have, as long as you can get a v, which we already got, so maybe I'll start highlighting these as I go, then all I have to do is complete the integral of v times du, and I'll be good to go, and in theory, I can answer this question, right? Again, all of this just stemmed from being very clever about undoing the product rule from calculus. And so the way I like to remember this, right, because eventually, you're going to try and remember this formula, one of the many that we're going to have to memorize for this class. But the way I like to do it is I say, okay, u times v kind of goes like this, if this is how I set it up. So I'm going to say, all right, well, u times v, that's the first part of my formula. So I'm going to say, okay, well, that's going to be negative, right, there's a negative sign here. I just like to write it in the front. So negative x times cosine of x, right? That part there is that's my u times v part. Okay, so that's my u times v part is this. And then the next part of the formula, there's a minus sign. And then we need to compute the integral of v times du. And so again, the way that I like to remember this is I just draw a straight arrow to the right. It helps me when I need to remember this formula for quizzes and exams. And so, right, my v times du, that's going to be a negative cosine of x, right? That's my v. And my du just equals dx. And so what we basically just figured out is that this is all supposed to equal my integral of u times dv, which is my x times sine of x dx, right? So we're looking for this answer, and I claim that all we need to do is to finish this left-hand side up, and we will get it. And thankfully, right, the antiderivative, well, actually here, there's a couple things that can happen. First off, there's a minus sign and a minus sign here, which is going to be a plus. So maybe I'll go ahead and just make this a plus and deal with that now. And then all we need to do is to figure out the integral of cosine of x dx. And last time I checked, what function has a derivative of cosine of x? That's just going to be sine of x. So it turns out that this integral, right, the integral of x times sine of x dx ends up equaling negative x cosine of x plus sine of x. And what else are we forgetting on this thing? Let's make some space for it, because you cannot forget it when you are doing indefinite integrals, is this plus c, right? And this should be our final answer. And we can check this, right? We can check this. We can check this by taking the derivative. So let's do that really quick, okay? So if I were, if this is a true statement, then I should be able to take the derivative with respect to x of not only the left side, but of the right side as well. And last time I checked, at least on the right side, the derivative of an integral should just leave us with what's on the inside of that, integral. Okay, great. And then on the left-hand side, we have, let's see here, we have the derivative of negative x cosine of x. Okay, that's going to require the product rule. So the product rule says it's the derivative of the first thing, which is going to be negative 1, times the second function, so just cosine of x, and then plus the first thing, which is just negative x, and then times the derivative of cosine, which is negative sine of x. And then we need to tackle the derivative of sine of x itself, which is plus cosine of x. And then we have plus c, but that derivative is 0. And so if we're careful, we're going to have a minus cosine of x and a plus cosine of x, which will cancel. And then the stuff that's left over in the middle here, these minus signs are going to cancel, and we are indeed going to be left with x sine of x. And so we're done, right? It turns out that this formula worked, and our integral is something that we can actually compute. Now, I know that one example is probably not enough for this, so let's do another example. Okay, so for example, let's do the integral of 2x e to the x squared dx. Right? Now, this one, you may be like, I got the product of two things, right? Let's use integration by parts. When you are solving for integrals, you should be careful. There's a good order of operations that we should do. The first thing that we should always do is, can we do it just by looking at it, right? Is there an easy antiderivative, right? And by easy, we mean, can I identify it just by looking at it? Or can I just do, say, the power rule? Okay, that doesn't work. The next step is to try the easiest integration method we have, which is a u substitution going to be working for us, right? Does u sub work, right? And it turns out in this particular case, it does, right? It does. And so a u substitution here is going to work if we let u equal x squared. Our du is going to be 2x dx. We will be able to solve this thing using a u substitution. And if those don't work, then step 3 is going to be try integration by parts, right? Start with the easiest method all the time, and then work up to the harder method. Okay. So let's see what we get here. So if we were to try and do this with integration by parts, I may try the same thing and say, well, let's let u be equal to 2x, okay? And then I would need my dv to equal everything that's left over, so e to the x squared dx. Now, the problem with this method is that at some point, I need to figure out what v is equal to. And the way that we get that is by integrating this thing on the left side and the right side. But the problem is there is no easy antiderivative for e to the x squared, at least not one that we will learn about in this particular class. You can Google it if you're interested, but this integral it's not something I can readily integrate. There's no u substitution I can do. There's no easy, the derivative of e to the x squared is not e to the x squared, so that doesn't work. And so, for this particular method, it turns out maybe we have to swap things around. Maybe we have to swap our choices. If I can't integrate one of these functions, right, then, but I can definitely integrate 2x. Let's try what if we let u be equal to e to the x squared, and let's let our dv be equal to everything that's left over, so the 2x dx. Let's try this. Let's see if we get somewhere. Okay. And so let's see, if u is equal to x squared, then du is going to be equal to, well, it's e to the x squared times the derivative of what's on the inside, so times 2x. And then our v is going to equal to, well, the antiderivative of 2x is just x squared. No problem. Oh, and I forgot my dx right there, right? When you take this derivative, little dx is going to pop out right at the end. So if we set this up, right, the formula says it's going to be u times v, which is going to be x squared e to the x squared, minus the integral of what we get going from left to right of our v du. And so here we're going to get, let's see, I have 2x times x squared, which is 2x cubed. And then I have e to the x squared and then dx. Now, I don't know about all of you, but this is even worse than the thing that we started with, okay? This one, very sad, very depressing. It doesn't end up being something that I can integrate very well. And so right at this particular problem, we have reached an impasse, which is that I cannot integrate this thing using the traditional integration by parts that you just learned, right? We do indeed have the product of two functions, right? I have the product of two functions, but I can't integrate them using integration by parts, because in both ways that we've done this thing, we've ran into a roadblock. So integration by parts fails us here, and we would need some alternate method, such as the u substitution, which was even easier than the thing that we just tried. But if u substitution didn't work and integration by parts didn't work and there wasn't an easy antiderivative, we'd either need some other sort of technique, or maybe this would be an integral that we could not solve. But let's see. Let's do another example. Let's do an example of one that actually will work out for us. So let's see. So for example, let's do the integral of the natural log of x dx. Now, this is an interesting problem, because the whole point of learning about integration by parts was that, if we have two functions being multiplied together, then we can try out integration by parts. That's the key thing. And we should run through a little checklist of one, is there an easy antiderivative for this? Can I just use the product, or excuse me, the power rule? Can I just do that? The answer is no. Can I just do a u substitution, right? Is there a u? Can I let u be equal to something in this problem? The answer is no. And so the next technique that we have up would be integration by parts. The problem is here is that it kind of looks like there's only one thing here, right? It looks like there's only one thing that we have here. How on earth could I use integration by parts? Because I'm supposed to have two things being multiplied by each other. Well, you just need to adjust your prescription. We do have two things being multiplied by each other. Now, when it comes to picking what's going to be our u and what's going to be our dv, we need to be a bit careful, in the sense that if you were to say let u be equal to dx, we'd run into a couple problems. First of all, it would mean that our dv would be equal to the natural log of x. Okay, this leads us to two issues. Number one, I cannot just throw an integral here because I do not have a dx here. Okay, if you're like, well, Dylan, let's throw a dx on both sides of this and call it a day. Well, I don't know about you, but what does the integral of dv dx equals integral of natural log of x dx even look like? Right? This is even a problem because the whole point of this problem is that I don't know how to integrate the natural log in the first place. So why would I let dv be equal to the natural log when I don't even know how to get this answer? And on top of that, what the heck is even the integral of dv dx? On top of that, there's the other problem, which is, what the heck is the derivative of this, right? If I take the derivative with respect to x of both sides, the left side, if I take that derivative and I take the derivative of the right side, what am I going to left with? I'm just going to be left with like du dx, and then on the right side, I'm just left with what, d? Like, this doesn't even make any sense, okay? So this particular way doesn't work if we make that choice for our integration by parts. So we're going to need to make a better choice, which is that, well, I may not know the integral of the natural log of x, so it doesn't make a good sense to, pick that to be my dv. Let's try letting my u be equal to the natural log of x, and let's let my dv be equal to everything that's left over, which is just my dx. Now from here, we can make some progress. We're going to get that du is equal to 1 over x dx, and we're going to get that v, the antiderivative of both of these, is just going to give me x, and now we can use the integration by parts formula that u times v, which is just going to be x times the natural log of x, minus the integral of what I get going from left to right here, my v times du, which I'm going to get x multiplied by 1 over x, which is just going to leave me with dx, and this problem, x times the natural log of x minus the antiderivative of this, which it looks like there's nothing, there's actually a 1 there, don't forget, is just minus x and then plus c. And we are good to go. And again, you should get in the habit of checking that this actually works, and that this is an answer to this particular integral. So I guess one more example that I'll do, I don't want to do every single example, because part of the fun of integration by parts, or maybe not fun for you all, but part of what really makes you a better a math student and just be able to do this stuff on your own is, looking at problems that don't exactly look like they use integration by parts, and being able to to kind of finagle your way through it. So for this last particular problem, it's going to look something like, let's say, let's do e to the x times sine of x. This is a solid problem. E to the x times sine of x dx. Okay. Now this one's interesting because I can take the derivative of both of these, and I can take the integral of both of these, so there's not really a clear-cut, way of which way that I want to be doing, the integration by parts. Like, which one do I want to let u, which one do I want to let be dv? So since there's no real rhyme or reason, I'm just going to say let's let u be equal to e to the x, and let's let my dv be equal to everything else. So sine of x dx. Now if I do this, thankfully on the left side, I just get that du is equal to e to the x dx. And on the right side, I'm going to get that my v is equal to the negative cosine of x, because the derivative of cosine pops out a negative, so we need to undo that. Now, if I do this, now I'm going to go diagonal, right? I'm going to get negative e to the x cosine of x. And then I'm going to have minus the integral of what I get going from left to right. Now, there is a minus sign here already to go along with this minus sign, so I'm actually just going to deal with that right off the bat. I'm going to put a plus sign there. But now we have e to the x cosine of x dx. And again, I miss and match. I like to put my e to the x first, followed by the trig function, and then followed by the dx. You can write it in whatever order makes you feel happiest. Now, the problem with this particular method is that, we're supposed to be solving this, right? So remember that all of this is supposed to equal, right, the integral of e to the x sine of x dx. But the problem is that I need to evaluate this integral. And this integral looks, just as complicated as the one we started with. But let's keep going. Let's try one more time, right? Like we're in the section, so we might as well try. Let's do one more. So let's, at this step, right, let's pick u equals e to the x again. Right? And so that's going to make du is equal to e to the x dx. And I'm going to let my dv be equal to cosine of x dx. I'm going to get my integral of cosine is just going to be sine of x. And so we're going to do the same thing again. So we're going to get, let's see here, we get e to the x sine of x minus the integral of what we had before, so e to the x sine of x dx. Now, I'm going to put this all in parentheses because I would like to remind you that this is what this integral is supposed to equal. So when you're doing your homework, don't forget to use parentheses, because or else what's going to happen is you're going to have a minus sign here and you're going to wrongly distribute things in. This happens all the time, so just don't make that mistake if you can help it. And so on the left-hand side, I'm just going to write everything out. So on the left-hand side, I have this negative e to the x cosine of x. And then we have plus, and then all the stuff that's inside this parentheses. So plus e to the x sine of x minus the integral of e to the x sine of x dx. And this is all supposed to equal my integral of e to the x sine of x dx. And you may notice something that seems a little bit alarming, which is I have now the same thing on the left side as I do the same thing on the right side. I feel like we did integration by parts, but we've done it twice now, and we have gone full circle back to where we started. And so you'll notice in these sorts of problems where we have two kind of cyclical functions, some functions that, their derivatives will repeat after some period of time, this kind of can happen. But I would say, all hope is not lost, and in order to be able to finish solving this problem, it requires a very slick trick. So I'm going to draw your attention to the right-hand side of the screen here, which is if I were to give you a problem that looked like -3 plus 4 minus x is equal to x, how on earth would you solve this problem? Would you just give up? You'd be like, well, there's an x on the left side, there's an x on the right side, I'm toast, what do I do? I'd say, well, no, I'm going to get everything that has an x in it on one side, and I'd get, and maybe simplify this, so I'd get like 1 is equal to 2x, and then how do you finish solving for x? You divide both sides by 2, and we get 1/2 is equal to x would be our answer. And so with this very simple algebra tool in mind, we can do the same thing here, which is I can take this and add it to the right-hand side. And by doing so, what am I going to be left with on the left? If it's okay with you, I'm going to swap the order of these just because I always like putting the positive term first. You don't have to. You can leave it as is. But I'm going to write e to the x sine of x minus e to the x cosine of x. And that's going to equal to 2 of these integrals, right? Integral e to the x sine of x dx. And remember, the whole purpose of this was to solve for this thing. It was to get this equals stuff. And we're practically there. The very last step here is we're going to divide both sides by 2, which I'm just going to erase that 2 and pop it over here on the left-hand side and say that this right here is my final answer, and we have achieved the goal at which we have set out to do. And so, yeah, I mean, again, you should verify this, and if you're just doing this for practice, you can plug this into a derivative calculator to verify, or you should do it by hand just to check your derivative skills. But it does turn out that if you take the derivative of this thing, you are just going to get e to the x sine of x, and then it's going to work. And so, yeah, that's going to pretty much do it for this integration by parts video. I'd say one last thing that people like to ask is, going back to the very first example we had, integral of x, sine of x, something like this, dx, and then we had the problem that we got stuck on, which was like 2x, e to the x squared, dx, and then we just had the one that we did, which was like e to the x, sine of x, dx. And people always ask, how do I know what I should be picking for my u? How do I know what I should be picking for my dv? And the answer, at least at this part, since we just learned this, is that there is going to be no shortcut for right now. In the future, you're going to follow those steps where the first thing that you should do for all of these is say, can I take these antiderivatives? The answer is usually no. And the second thing that you should ask is, okay, can I do a u substitution? And that kind of checks this one out, and we don't even need to try integration by parts. And so if we're just looking at the last ones, the question is, well, what should I pick for my u? What should I pick for my dv? Typically, it's a good idea to let your u be the thing that's going to get simpler over time. So, if you were to scroll back in the video, you would have seen that we got u was equal to x and dv was equal to sine of x dx. And the reason why I made this decision is because I know that if I take the derivative of x, what's going to happen to it as I keep going, right? The derivative of x just becomes 1. And if I needed to do integration by parts again, the derivative of 1 would become 0. And the whole point is that as I take this derivative and I get du is equal to dx, this first term becomes simpler, or in this particular case, it gets completely eviscerated. And so if I had picked the wrong way, and by wrong way, I simply mean if I had said, let's let u be equal to sine of x, and let's let my dv be equal to x dx, then on the left-hand side, on the right-hand side, we're going to get v is equal to x squared over 2. And on the left-hand side, I'm going to get the du is equal to negative cosine of x dx. And this doesn't really help us because when we set up and we follow our little thing of u times v, I'm going to get x squared over 2 times sine of x minus the integral of negative x squared over 2 cosine of x dx. And now I've just made my life even more complicated because now this polynomial term up here is going up in degree, right? Now I don't have an x to the first, I have an x to the second. Now I have a cosine, right? And this is all bad. So for cyclical functions, it doesn't really matter which one you pick. But in ones like these where you have the opportunity to pick a function that could become simpler if you take its derivatives, it's usually a good idea to make that selection. Yeah, so that's going to do it for this video. When you're done with this one, you can head on to the next one where I'm going to introduce you to a slight shortcut that makes solving integration by parts a little bit faster for a very particular type of problem.